Ambika, along with my co-author Sangeeta, will be presenting our research paper on analyzing the acoustic performance of unglazed terracotta in an indoor office environment, also co-authored by our professor, Amalan Sigmund Kaushik. Noise is a concerning and prevalent issue in the built environment. Office spaces are subjected to multiple noise interruptions during work hours, like HVAC noise, background noise, human interaction, and so on. Acoustic panels are a highly efficient method of noise control in the built environment. However, most of the acoustic panels available in the market today are unsustainable and have been discovered to adversely impact human health. Terracotta, an indigenous and durable material ingrained in the vernacular architecture of India for centuries. It is conventionally used for roofs, floors, and decor, but remains unexplored for its acoustic properties. Through this research, we aim to evaluate the acoustic performance of unglazed terracotta tiles as a salutogenic resource using the reverberation room method and impulse response method in an indoor office space. This research aims to encourage architects to consider terracotta as a prospective material for building acoustics. We intend to explore the architectural acoustics of unglazed terracotta, a sustainable and locally available material for increased quality of work and health in an indoor office environment. The two primary objectives for the research are to perform a comprehensive measurement of the acoustic properties of unglazed terracotta with a sound level meter and make a comparative analysis of the acoustic quality pre- and post-placement of terracotta specimens in the office. Coming to the materials and methods. It is crucial to design all spaces sensitive to acoustics, not just dedicated to musical and speech spaces. Nowadays, a greater attention has been focused on sustainable building methods. This comes with analyzing the acoustic and thermal performance to achieve a significant impact on the environment and human health and exploring sustainable acoustic options. Unglazed terracotta has high porosity in comparison to the commercial glazed wall tiles, which makes it a viable option to explore as an acoustic material. Coming to the methodology, the acoustic comfort property of unglazed terracotta is explored to analyze how the material influences the overall acoustic quality of the space. The scope of the research is identified through literature review. Parameters such as sound absorption, background noise, sound pressure level, speech transmission index, reverberation time, and noise curves are meticulously measured both pre- and post-placement of terracotta specimens using a Bedrock SM90 Class 1 sound level meter. Calculations are made using existing standard formulae like the Sabin's formula to understand the absorption coefficient of the tiles. An overall evaluation of unglazed terracotta is done to understand its acoustic properties. Standard tests are performed to analyze the acoustic property of unglazed terracotta. Reverberation measurements are carried out as per the standardized procedure given in the ISO 33822. The impulsive response method is performed for reverberation time RT60 measurement with the help of a clapper to measure the decays at the 1/3 octave band. The energy decay curves were then plotted. The measurement was taken multiple times to ensure accuracy. Speech intelligibility is measured with the STIPA Pro to measure the speech transmission index. A measurement of 60 seconds was taken to improve measurement accuracy. The STI analysis was carried out at a 1/3 octave band from 125 Hz to 4000 Hz. Background noise is measured using real-time analyzer at the 1/3 octave band to analyze the frequency values from 25 Hz to 20 kHz with a measurement time of 60 seconds per reading. Signal to noise ratio is measured to the sound pressure level of running speech. Each reading is taken for 60 seconds and a talk box is used to produce a sample running speech. The SPL of speech and background noise are calculated as well as the total LAEQ. The signal to noise ratio is calculated with the obtained value. Noise curve is measured to evaluate the noise levels based on sets of standardized spectral curves. Noise criteria standard values were derived to evaluate the background noise in the room. Coming to the equipments used, the experiments are measured with the help of the sound level meter Bedrock SM90, which conforms with Class 1 requirements. A fabricated clapper is used to measure impulse noise, and a talk box is used to dissipate sound during the experiment as per the requirement. Coming to the site location, the study was conducted in an office room on the second floor of the Department of Architecture at the National Institute of Technology, Tiruchirappalli, Tamil Nadu, India. The office measures a total area of 101 square meters. The existing office space had two windows on the 0.9 meter sill level and stack ventilation windows. Coming to the experiment, it was carried out in two phases. Phase 1 being the base case pre-placement of terracotta and phase 2 being the post-placement of terracotta. The base readings were taken from the office room in 6 different locations of 1.5 meters apart. A fixed microphone placed at a height of 1.2 meters is used for the measurement. A total of 10 decays are taken from each microphone position, giving us a total of 60 decays as per the ASTM standards. For the second phase of the experiment, readings are taken post-placement of 100 5-processed unglazed terracotta tiles of 0.625 square meters each. As specified in the ASTM standards, the tiles are laid out on the floor for convenience of measurement in an asymmetric pattern. 60 decays are recorded in a similar manner to that of the base case.
The background noise was measured first. The types of background noise identified were from the fans in the room, noise from the students and staff members from the floors below, and the noise from outside the building. LAEQ, LAF max, LAS max, LAI max values across frequencies 125 Hz, 250 Hz, 500 Hz, 1000 Hz, 2000 Hz, 4000 Hz, 8000 Hz and 16000 Hz were taken, and the values have been provided here in the table. The measuring equipment was carefully placed 1 meter away from all surfaces and at a height of 1.2 meters from the ground as per standards. The next test was to identify the sound absorption coefficient of unglazed terracotta, for which RT60 values were measured. Using the sound level meters, RT30 and RT20 values were taken across 6 locations, 10 readings each with and without terracotta. These values were converted to RT60 and plotted in the graph format. This is the table and the graph of RT30 with terracotta. Next we have the values of RT30 with terracotta. As you can see, the RT30 values have reduced from the base case where terracotta was not placed in the room. This shows that terracotta has potential to become an acoustic absorber. The calculation of sound absorption coefficient was done using the Sabin's formula across different frequencies. Additionally, the noise reduction curve was also calculated and identified to be 0.063. The next test performed was the speech intelligibility test using STIPA. Speech intelligibility refers to how comprehensible the speech is to the listener. For an office environment, a value of 0.3 to 0.45 is considered poor, while 0.45 to 0.6 is considered fair. In this case, we can notice that there isn't much change in both cases, especially the further away the listener is from the sound source. The next slide covers the signal to noise ratio or SNR values. It is a measure which is used to compare the level of a desired signal to the level of background noise. Increased in SNR value is a good sign, as it means that the speech is more clear to the listeners. The next slide covers the noise criterion test. It is a new rating system that takes into account the distribution of noise energy across various frequency bands. The table below shows the recorded values. From these tests, we can conclude that unglazed terracotta is a textbook panel absorber. Once made into a product like wall and ceiling panels, with proper backing and coating, it has huge potential to function as a sustainable option for acoustic absorbers. Thank you so much.